What you see here are living bacteria. They could soon be used as a construction material in buildings. As a starting point, a common type of soil bacterium has to be revitalized in a mixture of urea and nutrients at a constant temperature of around 30 degrees Celsius.
Inside this mix, bacteria starts to develop. They basically grow in number. The bacteria has to reach a certain quantity in order to make cement. After around 3 hours of fermentation, our mix is ready for use.
These scientists from a European research project then add the revitalized bacteria to a mix of sand, industrial cement waste and the ash of rice husks. Cement manufacturing accounts for some 5% of global carbon emissions, researchers say, and they want to prove that a greener, ecologically friendly cement could soon be available.
Our raw materials are basically all waste, so we don't have added costs. For instance, we don't need to extract and transport the limestone commonly used to produce cement. And we also save the energy costs.
In ordinary Portland cement, they have to use very high temperatures, up to 1,500 degrees, in order to turn limestone into the cement. That's part of the process. And that takes an awful lot of energy. Here, the bacteria multiply at 30 degrees. So that's a massive difference. And that amount of heat energy is saved because we're using a biological process to bind the particles together.
Bacteria bind the particles together by naturally producing calcium carbonate. Initial tests have proved promising. Researchers, microbiologists and chemists are working to help the bacteria become more efficient.
It's important to know the ideal density of bacteria in the mix. We've done research on that. We know, for instance, that greater bacteria density doesn't always mean that the product will be more resilient. On the contrary, sometimes beyond a certain point, too many bacteria can undermine the strength of a final product. So we need to find the optimal number of cells to produce the cement.
Preliminary results of ongoing tests on the material's plasticity, elasticity and resistance to stress or deformation are already showing the way for eventual applications.
We decided to use this material as mortar and not as concrete because it is not as strong as traditional concrete. But it can be easily transformed. That's the reason why we decided to use this material as mortar.
Whatever the final applications, researchers hope the new material could be a reality on European construction sites in less than a decade.